Thank you, Graham, for that very generous introduction. It's a great pleasure to have the opportunity to talk about my research to such a large and varied audience. The title of the lecture is Hidden Connections. What I'm going to try and do is show you how pattern analysis can be used to uncover hidden meanings in data and provide users, and by users I mean everyone in this room, with the information that we need. So there'll be three parts to the talk. First of all, I'm going to talk about hidden connections and the various ways that comes into pattern analysis. I'll then talk about how pattern analysis works in practice and the differences between, if you like, theoretical research and application-oriented research, which is what I mainly do. And if we have time at the end, I'm going to introduce some of the future directions in the field that I see coming up over the next few years. So, why are we interested in hidden knowledge? The reason is that we are surrounded by vast quantities of data, and understanding it is a real challenge. Why are these quantities of data increasing? Well, we're measuring more things. Remote sensing satellites are being used to measure ecology, meteorology, all sorts of data of that sort, and that data is growing, is increasing at a great rate at the moment. We're measuring more in medical records. So we're not just going to the doctor, getting a printout of a scan, and that being then thrown away at the end of the session. That's being recorded electronically and stored in electronic patient records. And that data is also building up, and we should be using it to understand disease better. So we're measuring more. We're also creating more information ourselves. I should imagine pretty well everyone in this room has used a digital camera or digital video camera. And you're storing some pictures and videos on your computer at home. And then the problem you have is, how do you find that picture that you really want to get back, simply given a large directory full of lots of files with perhaps not very meaningful names? We're all using word processors to create lots and lots of documents. Again, where's that particularly good passage that you wrote three years ago in a document? How can you find it again? And there's a greater diversity of data that we're being confronted with. We're confronted with attributes, rectangular tables like in spreadsheets. We're confronted with one-dimensional data where you're measuring a single variable over time. So, for example, when you measure ECG, you're measuring the potential differences in the heart. It's the same variable, but you keep measuring it 150 times a second, perhaps for a whole day. And then the question is, what's in that data? What can it tell you about your medical condition? Two-dimensional data, that'll be images, three-dimensional video, and so on. So we're surrounded by lots of data which we don't really understand very well. And we need some help to understand it better. Machine learning is the area of my research, and that's the computer-based generation of models from data. So the idea is that we're going to have models that help us understand the data, but we're not going to have to build them ourselves by hand. We're going to get the computer to do that for us. So if you like, the computer is generating all this data that we're struggling with, and we're going to use a computer to then help tame it and understand it better. What do I mean by a model here? I mean a parameterized function from input attributes to an output prediction. So it's a way of mapping a set of inputs to some prediction that we want to have. And the parameters in the model express the hidden connection between inputs and predictions. So here's a little example. Here I have some handwritten digits. So if you're in the post office, you'd like to be able to recognize handwritten digits automatically so that you can sort letters automatically. A model will take the inputs that you see there on the screen, so it will take the 784 pixels in this image, and then we'll make a prediction. And the parameters adjust what that prediction is. So if the parameters are right, then when I see an image like this, I get an 8 as the answer. If the parameters are wrong, I'll get a 6 or a 4. And so what we need to do is set the parameters correctly, and we do that by learning them automatically from data. So that's where the machine learning comes in. So what sort of things might you want to know? Well, one application might be you're sitting at home of an evening, and you decide you'd like to listen to some music, but you can't remember what that really good piece was. You can remember the main theme from it. So it'd be nice to be able to go up to a microphone, whistle tunelessly into it, which I won't demonstrate, you'll be glad to hear. And the the computer will say, aha, I recognize that. That's the main theme from Tchaikovsky's Sixth Symphony, and then start playing it over your hi-fi. You might be worried that you have a heart condition. You might be sitting at home, you could feel palpitations, and the question is, do you need to go and see a consultant cardiologist? Well, your GP can make an appointment, but it might be 6 months before you see that person. In the meantime, of course, there's a lot of stress from worrying about whether you're ill or not. Wouldn't it be great if you could go along to your GP, he could do a very simple analysis of your heart condition then and there and say, yes, it's of concern, we'll fast track you through, or no, it's fine, you don't need to worry about it. If you're working for a pharmaceutical company like my colleagues at Pfizer, they'd like some help in picking drug-like molecules that will help cure a particular disease. They screen millions of compounds routinely, and they want help with understanding that data so they can then pick the molecules that are likely to proceed to drugs in the long term. You might want to know how strong the wind is going to be tomorrow. So if you're in an insurance company, for example, is it going to be a hurricane or just a gale? You might want to know which genes are activated in a metabolic pathway, or what will be the price of the winter 2008 electricity contract next week. Should I buy contracts now, or should I wait till next week? So what do all these applications have in common? Well, first of all, we can't write down an algorithm that will solve them. There is no algorithm that says when someone whistles into a microphone, you apply these simple 20 steps of computer program, and out comes a selection of a piece of music. What we can do is we can gather data. We can gather input data, so people whistling into a microphone, and target data, which is the actual piece of music it belongs to, and try and associate the two. And this data has to be labeled by experts. So someone human has to come in and say, yes, this is the classification of this particular piece of music. All right, we can't write down an algorithm, but we've got lots of data. The standard computer science approach might be to say, well, what we'll do is we'll create a big database, we'll store all the possible things we're looking for, all the digits, all the pieces of music, and we'll simply look it up, look the answer up. Nice and simple. The trouble with doing this is that for many of the applications we're interested in, the number of possible examples is enormous. If we just take that simple example I showed you of character recognition, we have a 28 by 28 pixel image. We've got 8 grey levels. That works out to be 10 to the 190 different possible patterns. Unfortunately, there are only 10 to the 80 atoms in the universe, so the chance of actually storing that on even on the largest memory stick you can think of are rather remote. So we can't work that way. What we have to be able to do is to generalize from the particular to other examples. So we're going to take a large data set, we're going to train our model on it, and then we're going to try applying that model to new data, and in that way, hopefully classify correctly the whistling or whatever it might be. And we're going to measure the generalization by evaluating the model on independent test data. That's important so that we have confidence that it's going to work in the future. So we don't just plug the data straight in, we're going to take functions of the input variables to create features which capture the essential differences between classes. What that means is that for example, on the digit data, we can see that here we've got loops. So loops are quite useful for detecting 8s. So what we'll do is we'll try and see if there are loops in the image, and if there is, we'll say, yes, there is a loop. If there isn't, we say there isn't. And we'll use that information to go into our model rather than just the raw pixel data. But classes overlap, and there might be ambiguity. So here's a good example. On the right-hand side, there's a handwritten digit written by a real person. And the question is, what digit is it? Is it a 5 or is it a 6? Oh, good. Someone said 6. That's right. There is some ambiguity there about which digit it might be. So we are going to be faced with uncertainty and difficult to resolve cases. And the important thing then is to incorporate as much prior knowledge as possible. So we know what digits look like, so we know we're going to use that information to help us build our models.